Hi, welcome to the 13th annual meeting of the eBeam initiative at the SPIE Advanced Lithography Conference. And I'm Aki Fujimura, CEO of D2S, which is the managing company sponsor of the eBeam initiative. So this year, I have the great pleasure to introduce QY Mask, which is a new mask shop in China. Welcome, and we look forward to your contribution to the eBeam initiative in the future. So you can see QY Mask in the middle of the a very large, broad spectrum of companies representing all the way from design, all the way away from manufacturing, representing the semiconductor design cycle around mask making in particular. So we thank very much all of the members for helping us with everything, including making this session successful. But we also want to thank you for helping us with a survey that we did in January on deep learning. So we asked, please share with us whatever you are able to, you're allowed to share publicly about your efforts on deep learning. And many companies responded. The ebeam.org website contains the results already, so please go take a look at that. There were also many companies that responded saying, we're working on deep learning. Deep learning is important, but we don't have something that we can publicly share at this point. So I look forward to this list growing over time, and I'm hoping that we can contribute to everybody being inspired by looking at other examples on how deep learning can be deployed for their own businesses. So thank you to the members for responding to this particular survey also. So yeah, that's it for the introduction. Let's move on to the panel. You can see the excited crowd. They're not wearing a mask like they should, but that's okay. It's just a picture. All right, let's go on to the panel. Thank you. Welcome to the eBeam Initiative virtual panel at the 2021 SPIE Advanced Lithography. Today, we have the pleasure of speaking with Ezequiel Russell of Micron, Noriaki Nakayamada-san of NuFlare, Danping Peng of TSMC, and I'm the moderator, Aki Fujimura of D2S. So today, we're going to mostly talk about curvilinear shapes on mask. But let's start by talking about what's in all of our minds with COVID. How is everyone doing? What's happening with your companies? Are you all sheltering in place? Nakayamada-san, how is it going in Japan?
Yes, I think we are doing okay. We work remotely from home and occasionally go to the office maybe once per week or even less.
Yeah, and you have visits to your customers, or maybe some of your people?
No, yeah. I don't go abroad to visit customer site anymore. Yeah. But we are doing a regular web meeting with a customer, and it's working.
Yeah, yeah, good. It's amazing how we can adapt, right? Yeah. Danping, how about you? Have you gone to Taiwan at all? You're based in San Jose.
No, I haven't been to Taiwan since last March. So we have been working from home since March 15th, and it's quickly approaching 1 year. So this is this is amazing, right? So I'm looking forward to go back to office anytime soon. Okay, with the virus coming out.
Yeah. Hopefully we get vaccinated, right? Our turns are going to be coming up sometime soon, hopefully. And how about you, Ezequiel? I know Idaho had some issues, but I know Micron's been particularly diligent, right?
Yes, yeah. Micron has been very diligent in putting in place protocols. So obviously we have people working on site to keep the wafer fab moving, as well as those critical for operations. Myself, I've been in the office for a while and working from home another part of the year. So no travel, like it was mentioned. So it's been a different year for sure.
Yeah, hopefully next year's version of this is going to be not virtual and actually be able to shake people's hands. That would be great. Hope to be able to see all of you individually too. Miss all those dinner meetings. Okay, so let's talk about curvilinear shapes. First, talk about it in the context of masks. So this is a slide that shows the survey results from the eBeam initiative Luminary survey, where really an overwhelming majority of the people think that curvilinear masks are going to be in use, at least partially on each mask by 2023. That was a question that was asked. It's very striking because today not that many shapes are curvilinear on the mask, so that's a huge change in only 3 years that's being projected by the luminaries. So we'd like to talk a little bit about that. Let's first start with Ezequiel, who gave a talk about this subject a couple of times in this forum. Maybe Ezequiel, you can describe this slide that we're looking at.
Sure, yeah, my pleasure. Micron has been studying curvilinear shapes on mask for a while now. Being a memory company, we obviously look at the memory cores first. There's some advantages of having curvilinear shapes in the memory cores. We then looked at the what we call the input-output circuitry around the memory cores, which are very tight-pitched, more random type circuitry and logic, and of course the periphery. What you see in this slide here is one of our studies to illustrate what we find as a general rule with a simple test structure of 3 contacts in a row, what you see on the left-hand side of the slide. In this particular case, what we're showing here is that by leaving the OPC correction unconstrained and not being forced to Manhattan shapes, what we let the OPC algorithm, in this case an ILT type of model algorithm, we would let the correction go unconstrained, and by that we allow curvilinear shapes, as you see in the lower left corner of the slide. That picture in red is the mask, the 3 contacts and all the assist features around them. So dialing in the ILT recipe, we can toggle increases in either depth of focus or exposure latitude, but basically increasing the overall process window for the mask features that we're optimizing for. In this particular example, as you can see, there's an 85% increase in depth of focus as shown in the process window in the center of the slide. And what you see in the very far right of the slide is the PB band of these same 3 contacts for both the conventional OPC on top and the curvilinear OPC at the bottom. Maybe hard to see, but if you zoom in, you will find that the PB band is tighter in the case of the unconstrained shapes or unconstrained OPC, the ILT solution. And that's exactly what we want to see, is less process variation on wafer by having this curvilinear mask or curvilinear shapes on the mask. So again, a simple example where we're showing one of the benefits that we observe of allowing curvilinear shapes on mask, benefiting the process window on wafer.
Yeah, thanks, Ezequiel. So these are recent results, but Danping Peng, who is now at TSMC in charge of internal OPC, but he used to be the CTO of Luminescent, who really pioneered curvilinear shapes on mask. Maybe Danping, you can talk about this slide, which came from a presentation by Samsung and Luminescent a long time ago. I forgot what year, 2009, I guess, yeah.
This is 2009, yeah. The curvilinear mask and the name ILT, inverse lithography technology, was coined by Luminescent. In 2003, I actually joined Luminescent even before Luminescent got that name. So it's at the end of 2002. I started out by building a prototype, okay, using MATLAB, and then I demonstrate the animation to the VCs. Right, the VCs was impressed, and then we got the funding, and then we came up with this name by one of the founders, Dan Abrams, and then we start to build a team to develop the algorithms to actually using a mathematically rigorous approach to formulate the OPC problems as mathematical optimization problems. And we are using level sets so that we can represent the mask shapes, not using the traditional, polygons, but using the level set to embed the mask shapes as using an implicit method. And then we try to solve the inverse problems as optimization problems, and then we can demonstrate all kinds of weird shapes, and then later on it becomes less. I would say the ambitious, and we try to be a little bit more conventional. So my initial mask is actually starting from random bubbles, and then we can showcase that we can actually starting from random bubbles, we can still converge to a solution that print pretty good decent shapes. And then okay, so that is good to impress the VCs, but for production, we still need to. We do not want the mask to be too revolutionary. So if you look at the picture, starting from the leftmost, okay, that is when you do not put any constraint to the mask and let it evolve, and then you can see that. Okay, the main feature looks familiar, and then you get the rings, which is the astraps that the naturally appears during the optimization. And then when you go through the pitches, right, when you start from the very tight ones, and then you go to the looser pitches, you get a solution, right, with a bunch of rings, and then from left to right, we becomes more and more conventional. And then, so when you becomes more conventional, when you try to use Manhattan shapes, what you lose is the loss of a process window at a given exposure latitude. So starting in 2005, 2006, we start to engage with the leading foundries like TSMC and Samsung. This particular result was demonstrated at Samsung. So at that time, when we presented our results at the SPIE, it was like dropping a bomb. But there is also a lot of doubt, right? At that time, people are not ready for such a revolutionary the solutions. I think there are three major difficulties at that time. One is a long run time, right? So the IoT takes almost like 10 to maybe 20x longer times to get the results compared with traditional OPC. And the mask solution looks complicated. So it takes a long time to write. I think the other one is the MRC, right? So the MRC for curvilinear ones are different from the Manhattan ones. So there is a lot of doubts, and then over the years we try to address them. And I think today with GPU acceleration, so we can address long run time to get the IoT solution. With the multiple beam mask writer, we can write the mask with any complexity in a constant time. And also, I think with the acceptance of IoT mask solution in leading nodes, and then we understand, okay, what type of MRC rule we need to use. So it's simplified to like 4 rules. One is minimal CD, minimal space, minimal island, minimal holes. And then there is also, we do not want to see kinks and bumps on the shapes, which even multiple beam mask writer cannot resolve. So Anyway, so I think it's a long journey. So, and as I mentioned, the three hurdles that used to plague IoT has been largely addressed. I won't say completely addressed, largely addressed. So it's about time for IoT to enter mainstream, like high volume manufacturing.
Thank you, Danping. Yeah, so speaking of one of the enablers that you talked about is multi-beam machines, and Nakayamada-san, who's been doing VSP machines since even NuFlare was a separate company. So he knows a lot about that, and he's right in the middle of the multi-beam effort at NuFlare right now. So let's see, if you can, Nakayamada-san, if you can use this slide to explain a little bit about the difference between VSP and multi-beam and why it is that multi-beam enables these curvilinear shapes to be used.
Yes. Historically, the LSI design was very simple, like two squares on the upper left graph. But once ILT introduced, it's converted to very complicated shape. Like in the mid above graph, and to write such a curvilinear complicated shape, the shape has to be shrunk into the squares or triangles, like on the upper right figure. And the single beam writing has to write each small chunk of the shots, massive number of shots by just one beam. So the writing time was very long, and that was one of the biggest hurdle to enable ILT writing, like Danping-san mentioned. But when multi-beam was introduced, that restrictions was lifted off. The pattern is converted into the group of pixels, I mean the bitmap, by rasterizing the original pattern. And the number of pixels are constant and flat. So the write time should be constant, no matter how complex the initial pattern was. The biggest point is the multi-beam has massive number of beams, typically 262,000 beams to write the fixed number of pixels. So the write time has been greatly reduced compared to VSP writer, and ILT pattern comes into real for production.
Yeah, thank you. Yeah, so multi-beam being in production use is really a key enabler for being able to write these things. And multi-beam, though, has other uses too. But despite that, the Luminaries, the same Luminary survey showed that even for EUV masks, not just for 193 on the left, but EUV masks on the right, they believe that curvilinear masks are going to be utilized at least partially on every design. So that's an interesting thing. You would think that EUV is much more precise, so you don't need to go as much into curvilinear masks as you might need it for 193i. Danping, what can you tell us a little bit about the special needs of EUV and why this might be the case?
Okay, so let me first comment that the state of the status of IoT is that we are using a hybrid of mostly Manhattan shapes with some curvilinear shapes, right? So as a hotspot repair, and so people may question why even for EUV we still need the IoT. The answer is that for EUV, the adoption of EUV tool in high volume manufacture was delayed by many years, many generations. So when we actually introduce EUV into high volume manufacture, so the EUV NA 0.33 is actually quite low compared with the DUV, right, immersion. So even for EUV, we still need to use very dramatic mask corrections. And a lot of the times, the traditional Manhattan-shaped patterns is not good enough. You know, the process window, PV band actually suffers if we stay with the Manhattan shapes. And ILT actually comes into the rescue. I think there is some, we see actually, even for EUV, we see more benefit using curvilinear the mask. For EUV, you know, one of the biggest headache right now is local CD uniformity. And to improve the local CD uniformity, we need higher quality optical images to reduce the short noise. And ILT mask can actually improve the LS, image log slope. So that is one of the actually drivers to use curvilinear EUV masks.
Yeah, thank you. Ezequiel, what's your perspective on the need or maybe lack of need for curvilinear IoT in EUV processing?
Yeah, I agree with what Danping explained. And I think to add to that, not only EUV was late according to original roadmaps for adoption, but by the time that we as a memory company deploy EUV and try to extend the lifetime of those tools deployed into manufacturing before having to convert to the next generation high-NA EUV tools, you will want to use your full arsenal of tricks, of OPC tricks that you've developed for immersion lithography, also in EUV, because it makes sense to extend the use of the 0.33 NA tools for as many generations as you can. So no question that the OPC groups across the world are going to be using and looking at curvilinear features as a way to extend the lifetime of those tools that are going to be deployed in manufacturing. That's number one. Number two, not only EUV requires all the image contrast possible, like Danping explained, in order to minimize LER due to shot noise. But in addition, what we find is that for small features that EUV will be patterning, especially when you have two-dimensional features, it does help the mask local CD uniformity as well to have curvilinear shapes, because the way the mask is processed, it helps with the overall consistency of those features by not having to resolve sharp corners that will have more variation, and thus contributing to local CDU on the wafer as well. So I see that there's multiple benefits. In my mind, there's no question that it'll be adopted. Timeline, I'm not so sure, and to what extent will depend on the application. Logic companies or foundries may have a different need than, for example, a memory company, just based on the patterning that we're doing, but no question that parts of the mask will see curvilinear shapes for UV as well.
Oh, okay. Thank you very much. It's a great explanation. So Nakayamada-san, let's look at this slide, because this is talking about the mask side. The question for you is, this is basically saying that the reason why people say they want to use multi-beam is mostly because of EUV, curvilinear or not. And then the secondary reason, or number 3 and number 4 here, they're talking about curvilinear. So EUV comes first before curvilinear for either 193i or EUV. Is that consistent with what you're seeing in when you talk to your customers?
Yes, it is consistent with what I discussing with customer. Number one factor is more throughput to EUV masks. There's one more factor in addition to the shot count factor I explained previously, which is exposure dose. EUV mask requires very high dose resist, low sensitivity resist, to reduce the shot noise, stochastic factor of the number of electrons. And to get better CD uniformity, we have to give more electrons and result in high dose. And the single beam writer has to increase the pass count to reduce the so-called resist heating effect to get better CDU. And increased number of pass count results in even longer write time. So, but multi-beam writer uses very small electron current per beam. So resist heating effect is basically doesn't exist. And it can increase pass count by a sophisticated writing strategy. So that's one of the greatest benefit of multi-beam writer for high dose resist, low sensitivity resist, without sacrificing the throughput. And the number two factor, more precision. Due to the increased pass count, it can get better placement accuracy. VSB single writer, maybe 4-pass writing is the maximum we can go, but multi-beam writer uses 16-pass. So it is beneficial in getting better placement accuracy by a higher number of pass count.
Yeah, great. Okay, thank you. Thank you for the help to understand what's going on here. That's great. So would you say that since for EUV, they're going to have a multi-beam machine anyway, because of what you said about resist heating and all those things, then there's no barrier from the writer point of view to also do curvilinear shapes on EUV, right?
Yes, partially true, because as I shown previous slide, the number of pixels are fixed, and it is regardless of the initial figure shape, no matter whether it was Manhattan or curvilinear, the total number of pixels is same. However, the density of the figures may be much higher with ILT pattern. That means the distance between the figures may be closer. Then we have to reduce the beam shot size to guarantee the space between empty pixels between the figures. That means we have to adopt smaller beam size, and smaller beam size dramatically degrade the write time or throughput of the multi-beam writer. And to cope with the increase of write time, multi-beam writer has to adopt more beam counts. And that's a very challenging task for multi-beam development.
I see, interesting. Okay, but do you think it's still going to happen? But what you said is true even with any OPC on EUV. Is that true? Or it's only for curvilinear?
I think, Aki-san, you may have answer because you are design and EDA expert. Yes, but it depends on the average distance between the figures, whether it's ILT or normal OPC of EUV. Right. If you concern only with a line end to end, maybe it doesn't suffer much.
Right. So it's about spacing and shape size rather than about the shapes, right? It doesn't matter what shape it is. It's more a function of how wide the shapes are on mask and how far they're separated, right? Yeah.
Yes, social distance.
Okay. Right. Social distance. All right, thank you. That's a topical question, but one I like to avoid, I guess, as much as possible. Okay, so let's go to the next slide. This is a related question. We also asked the luminaries about how it would be used. Some of you touched on it already, but is it for all, the entire critical layer is going to be all curvilinear, or is it going to be only some of the selected more difficult, say, critical layers, or is it going to be critical layers, very few critical layers, how much is it going to be used? And then the question beneath this is it only used for hotspots, like Danping was suggesting is done now, or do you think that it's going to be used for the entire layer? Maybe Danping, you can go first and give us some insights on what you're thinking.
I think in the near future, so we only a few critical layers will use IoT for hotspot repair, and we probably will see an increased use of for IoTs in maybe into 3 to 5 years time frame, and as to move to full chip. Obviously, there is a price to pay, right? The runtime, we need to address that. And as I mentioned before, the GPU can largely address this. And then there is also the psychological effect, right? Many of the OPC engineers, they have been very familiar with traditional Manhattan-shaped OPCs. Then moving on to GPU-based IoT, there is hardware, the issues. There is also the IoT, the recipe issues. I think we have some issues to resolve, but there is no showstopper. When we move to full chip, we do not need to do the dissection, the traditional way to do the dissection, and then maybe we can get actually more uniform mask solutions that have a larger common process window across the full chip. So that's some of the benefit I think we'll see. We already see it on the critical layer on hotspot, right? So I think when you use it to full chip, definitely we'll see a more benefit.
Yeah, good, thanks. How about your feelings, Ezequiel? Hotspots versus the entire layer.
Yeah, I agree. I think hotspots is how the industry is starting to deploy curvilinear solutions. Primarily, I think because this was done prior to multi-beam being available. So writing a full chip was prohibitive if all features in the mask are curvilinear. So it made sense. A repair flow where you can introduce all the flexibility to OPC that you can to repair that hotspot wouldn't have a negative effect on the right time using variable shape beams. Now with multi-beam becoming more of the norm, I think that you'll see more and more transition to full layers or full chip for critical layers. Not all critical layers will require curvilinear. I think that probably be overkill, but certainly there will be layers where it makes sense to deploy it more broadly than just hotspot fixing. Now, I think what you'll see is immersion reticles will take advantage of this first. And as K1 becomes more critical for EUV layers, you'll see EUV will follow. I can see the same trends developing, just spaced in time a little bit.
Okay, great. Yeah, thank you. So we alluded to some other aspects like runtime, but I think there might be other barriers that people think about in the mask ecostructure for, is everything along the way ready for curvilinear shapes? Maybe Nakayamada-san, you're in the mask community, so do you have a comment on what inspection, writing, metrology, like, is everything else going to be ready? Is it just the writer being multi-beam that's needed?
This is an interesting topic. 5 years ago in 2016, there was a backcast panel discussion about the exact same topic. Which one will be the showstopper for the introduction of curvilinear ILT? And I thought there was 8 panelists, so it was a very big panel, and I was one of the panelists. But I remember nobody said, yes, I am the showstopper. So everybody said, we are ready to do curvilinear writing, mask manufacturing. And but it's already 5 years since then. So I think it's a good topic to discuss one more time this year. After the introduction of EUV and after the mature development of IoT technology, including multi-beam mask writer.
Yeah, thanks. Ezequiel, are you seeing any barriers, other than multi-beam, other than GPU accelerated stuff? Like what do you see?
Yeah, I don't see a major showstoppers, but I do see there are some gaps. Particularly, I'll focus on the mask data prep, which is more of my area of expertise. Certainly, I think the industry will benefit from having a standard for curvilinear file formats. I know that's been in development, but not yet widely adopted. So certainly having a language or a file format that different tools can communicate. I mean, Oasis file format has been the standard for such a long time now. But unfortunately, for highly dense curvilinear shapes, Oasis is probably not the most efficient file format for that. So having a widely supported protocol or standard for mask data will help the interoperability of the different tools across the tape-out process, including going into the multi-beam mask format as well. So I think the whole process will benefit from that. That's the gap I'm seeing today.
So data path is a main component. Danping, how about you? Like if you're advising somebody trying to start a new company or something, like, is there an opportunity here?
I think I want to maybe add my own perspective. So the mask data prep, we already mentioned the file sizes. So we mostly see the file sizes increase on at the fracture stage. So what I'm thinking is that for curvilinear mask, we may need to do something different. Do we really need to do the fraction for multiple beam mask writer, right? This is after we do this IoT, we give the curvilinear mask shapes, and then maybe we can use that one to generate the dose map and then directly send it to the multiple beam mask writer. So I think maybe we can skip the fraction step. This is one. The other one is, I think, for curvilinear masks, the traditional, like the mask inspection and mask review in die-to-database mode. I think maybe the vendors need to get ready to model the curvilinear mask. From my own experience, curvilinear mask is not more difficult to model, actually. Mostly mask 3D. It's only that many of the vendors probably they are still like in the model they still use some Manhattan shapes, right? The vertical horizontal edges, and those approaches definitely is not applicable for curvilinear mask. So they need to look for different approaches. It's not that difficult, but it's still some work need to be done to support the die-to-database mask inspection and mask review.
No, thanks. Yeah.
In addition, I was going to add that going upstream in the design flow, I think design tools that support curvilinear target shapes is also quite important to close the loop. We've been
That's a good point.
Mostly focusing on what happens downstream in the mask data prep and going into the multi-beam writer, but I think, like we discussed earlier today, there's a benefit of starting with curvilinear targets, not just converting to curvilinear when you do OPC or IoT. So support on the design space for curvilinear shapes, I think it's important as well.
Oh, that's great. It's a huge opportunity there for sure, right?
Yes.
Okay.
Yes.
Great. Yeah.
We can leverage the extra freedom, for on the design, right? Mask, we already have reached a consensus that we need to go to curvilinear. And on the design level, I think we also need to go to a curvilinear to get the benefit full benefit.
Yeah, we'll come back to that at the end for a little bit. But let's stay on the theme that you were on there about processing time. This is the mask maker survey by the eBeam initiative that we do every year. And turnaround time is obviously an issue as you go more and more finer geometries. It just takes longer to process. The main picture here looks like it goes down at 7, but the normalized picture on the yellow is really more what the actual trends are if you look at it on a per company basis. You would think that maybe Curvilinear is going to increase the number of vertices that have to be transmitted and processed, and because of that, it might go like jump way up high, which would be obviously a big problem. So that would be a concern, and I think that's why you both mentioned that Curvilinear format is an important aspect of it. Are there other things, other mitigating factors? Like what are you seeing about turnaround time as an issue, Ezequiel?
Well, certainly processing a full chip with IoT engines and models require extra time. It's a longer process than the conventional OPC. Normally, what we've done in the past, as the ground rules became smaller, technology nodes needed more complex OPC algorithms and recipes, we've been mitigating runtime by adding more horsepower, meaning more CPUs and distributing over larger and larger farms as a way to control the growing runtime. But certainly IoT is a step function there. And adding more CPUs, even though possible, it brings other considerations, space, power, and just the linearity of the whole process, and not to mention that having to distribute in smaller template sizes cause some template boundary issues that then needs to be fixed. So it adds some overall inefficiencies to the process. So one of the new trends we're seeing, obviously, is the use of GPU. I think Danping mentioned this before as an enabler for IoT, especially on large scales. So for full chip OPC or IoT processing, certainly GPU is an enabler and a trend that we're seeing in the industry right now.
Great, thanks. Danping, you're a computer scientist, right? So a GPU and how it computes, and also how Multibeam writes masks, and you obviously are one of the creators of how Curvilinear IoT works with that. So maybe you can comment on this aspect of it, turnaround time.
So as I said before, the multiple beam mask writer can write mask with any complexity, in a constant time. So the write time is not a problem. So what I see that the increase of turnaround time is mostly from the IoT runtime, right? So it's not the write time; it's the runtime. And so far we are at the threshold of using GPU to do the IoT, but it's not a reality yet. I know several vendors is working on that. We are also looking into this. So I think pretty soon we are going to see the IoT runtime decrease dramatically. So and then of course if we can address the file sizes and then the file transfer time, and also the data prep time can also be addressed. So I don't see a showstopper or dramatic increase. We have ways to address them. It's only that we have to make sure that the whole infrastructure, the whole the integration system is there. So I think we are very close to have a practical solution that does not increase the turnaround time significantly, compare with traditional Manhattan OPC running on the CPU. Of course, traditional OPC time can also benefit from GPU, right? So at that time, when you compare using the GPU, IoT will always be more expensive when you use the same hardware infrastructure. So, but at least does not become too long that the people has to wait for weeks for IoT solution. Okay.
Right. Yeah, that would be a problem, right? So, okay. Let's talk about MVP time. Nakayamada-san, I know you have some thoughts about that.
Yes, here I articulated the multi-beam data processing flow from circuit design to the mask writing. And like Danping-san mentioned, or Ezequiel-san also mentioned, OPC-ILT part is taking most of the time of the TAT. But here we propose another TAT reduction after OPC-ILT. So historically, after OPC-ILT, there is a mask process correction step, MPC step, before the fracturing to the writer format. But we propose to move complex part of MPC from pre-writing fracturing, pre-fracturing step to the inline multi-beam writing process. So there you can see that the data is divided into two flows, rasterized only or rasterized and MB model-based MPC to create a bitmap data to be provided to writer. And this rasterizing makes bitmap data anyway. And if pixel bitmap data is available, we can do complicated model-based MPC on the writer's data path to remove some of the burden from the pre-fracturing MPC step. So MPC before fracturing can focus on only the rule-based simple correction, while putting the more lengthy process or step to the writer's inline data path to speed up the turnaround time.
Yeah, doing it in line as the machine writes definitely saves time, right? Okay, yeah, thank you very much. Doesn't the whole problem though get worse with EUV? EUV has more data on the mask, so you would think that all of the data path problems are going to be exacerbated with EUV. Is that true? Is that a concern, Ezequiel?
Yes, that.
Oh, sorry. No, sorry, Nakayamada-san. Go ahead, Nakayamada-san.
Yes, that's true. There are two problems. On the geometry figure side, the left-hand side of the flow, and pixel data volume problem on the right side. But as I mentioned, number of pixel data is fixed and constant. So, and it doesn't scale up at all. But number of figures on the left side scales up as the EUV resolution gets smaller. And processing such a huge count of figures and huge count of vertices in case of ILT becomes a problem. And as both Ezequiel-san and Daniel-san mentioned, there was a proposal for the more efficient expression of the curvilinear shapes to reduce the data volume. Yes.
Good. So, Ezequiel, go ahead.
Yeah, I'd like to add, I agree with what Nakayamada-san just explained, and just to add a couple factors that come to my mind specific to EUV. First one is that we are adopting EUV to simplify some of the patterning steps that are now multi-patterning, either through pitch multiplication or some other sort of multi-patterning technique. So it's natural that the number of features on mask will double or more than double, just because layers that require multiple masks to pattern before, or multiple process steps to increase or reduce the pitch on wafer, are now single pattern using UV. So all those features end up on the mask. So you have a factor of 2 automatically there. The other thing that we need to consider is that the EPE, or the edge placement error budget, that the OPC teams have going into UV is much smaller. That requires us to use finer grids, which increases data volume, and that in turn requires more processing time through the tape-out flow.
Right. Danping, anything you want to add?
So for curvilinear mask, I'm thinking, can we skip the fraction step, right? So we send the curvilinear mask directly to the multi-beam mask data prep, and then they do whatever they wanted. And I do not see a need for fraction. So maybe I think the NuFlare and MS, they can work together, or maybe come up with something that so that we can skip the fraction steps, because that is where I see the file size increase. There is a way to address that, but so far we do see some substantial file increase at fraction step stage.
Yeah, good point. I think that's probably a part of the writer format discussion. Let's move on to that discussion. I first wanted to explain for the audience that's not familiar with the discussion, there's a curvilinear format group in the industry that Frank Aboud of Intel is leading. I think they're making some good progress, but the problem that they're trying to address is what I wanted to talk about. Today's formats are all piecewise linear polygons, even if they approximate curvilinear shapes. So they look like the blue shapes on the left. And if you have a sufficiently large number of pieces, line segments or vertices, then you can get arbitrarily close to the green shape that you want to get close to. If you have a much more abbreviated expression, like the one on the lower left side with the blue polygon there, you can get pretty close, but you won't be exactly right. If you look at it overlapped, the blue overlapped on top of the green, you can see that that lower blue obviously has a higher edge placement error, or EPE, as you go around the circle and measuring the difference between the blue and the green. There are larger errors if you try to abbreviate. So there's a trade-off between size and accuracy, and we could argue how much is needed, and how much data is there really contained in the output of IoT and so on. But nevertheless, the discussion here is that when you're targeting curvilinear shapes, and you need to inspect against curvilinear shapes, and you need to know how well you did, you need to know what the target is. And so isn't it better to come up with something that is more like the right, where you have a file format that describes a curve that has an infinite resolution, if you will. And there are known formats in the world that do this, like spline formats or NURBS formats that Jin-Chae at Samsung has talked about in the past. And so the discussion really is there a way to compactly represent something like an infinite resolution curves like the green by using some mathematical technique. And the blue dashed line on the right is representing a spline set of those are the vertices that are represented. And some formats have some additional data and all that to gain accuracy, but that's not really so much the point as the target is to be able to describe a curve. So people are working on this, but Nakayamada-san in particular has seen this problem come for quite a while now, and so he's actually published a number of papers about this. So maybe Nakayamada-san, you can talk about what NuFlare is doing with MBF 2.0.
Yes, to explain MBF 2.0, we start from traditional VSB 1212i data format. It accepted only trapezoids of 90-degree and 45-degree, so-called Manhattan shapes. We added any angle trapezoid in MBF 1.0, but after fracturing ILT pattern, as you see in the picture, the pattern is sliced into very small slivers, even though we adopted any angle trapezoid. By introducing polygon in MBF 1.1 format, we can reduce the data size from maybe by factor of 5 or 6. But as you can see, there's cutting line in between the whole pattern and the outer shape. And you cannot see this in this picture, but there are many, many vertices along the edge of the pattern. And we introduced whole and B-spline curve expression in MBF 2.0. And successfully reduced the data volume by a factor of 2 to 3 from MBF 1.1 baseline. This is assuming edge placement error, 1 nanometer tolerance. So if we want 2 or 3 more compaction of data, we provide MBF 2.0 format to the customer to meet that demand.
So this is using a B-spline, right?
B-spline, yes.
Yeah, okay, great. So Danping, what are your thoughts? Because you come from the OPC perspective, do you think infinite resolution curves are required to be able to handle curvilinear shapes?
No, I don't think we need infinite resolution like of the curvilinear mask. I think some reasonable representation that with acceptable data size obviously is going to facilitate the adoption of IoT mask. So I think this new data format is a positive move in the right direction. And we need to be careful that we reach this agreement with data prep companies like D2S, Synopsys, and also the inspection, vendors and other like downstream vendors, so that they can actually support this. We might need to reach an industry accepted data format and also provide a set of maybe reference implementations to encode and decode the data format, right? So that is something that I don't believe we are there yet. So today we are using the curvilinear, like a polygon format for hotspot repair. I guess as the area that need IoT increase, we will run into problems. So this is a data format is needed, and it's a welcome move. And I look forward to the industry and the vendors, ED vendors provide the solution. Right?
Yeah, infinite resolution isn't needed maybe, but if you can provide infinite resolution with approximately
that's
the
an
same
added
file
benefit.
size,
It's
might as well, right? Yeah.
Yes,
yeah,
it's
yeah,
an added benefit. It's an added benefit.
Yeah. Ezequiel, is the memory maker's perspective different?
I don't think it's different. I agree that infinite resolution may not be needed, but it's welcome for sure. Again, I think thinking the whole flow from design layout all the way to mass data prep, a solution like this will bring a lot of value. One thing that we haven't discussed yet is that this step of converting to B-spline curves may introduce, and going back to your question about infinite resolution, is it needed? I think that you need enough resolution not to introduce a new source of EPE error in this representation as a B-spline curve, for example. Since the ILT algorithm will be providing a fully curvilinear shape on a given grid, and then you're basically fitting this B-spline to those polygons. As I mentioned, especially with EUV or very advanced immersion layers, where our EPE budget is shrinking node to node, adding a new source of EPE is going to be a concern for sure. So minimizing that by trying to increase the resolution as much as possible is a welcome advancement.
Yeah, that's a great point. What Ezequiel is referring to is that the spline algorithms are not, they're lossy. There's a trade-off between how long it takes to encode and how accurate they are, right? So, you want to make sure that you're spending enough time in encoding it so that it's accurate enough. Yeah. So I think your point is accuracy is more important.
Yeah, I want to add something. We obviously need efficient encoding, decoding algorithms, right? And reference implementation to convert from curvilinear mask internal representation to the B-spline representation. There is another issues, or maybe it's an advantage that we need to consider. We may be using B-spline representation provide us a way to enforce the MRCs, right? Let's say we do not want to see kinks or bumps on the contour, right? I think B-spline usually is very smooth, right? You can actually compute the curvature of a B-spline very efficiently. This is a benefit. I'm not quite sure about how to check the CD and space by looking at the B-spline representation. Maybe you need to go back to the internal curvilinear representation. So anyway, we need to have efficient ways to represent the curvilinear mask in both worlds, right? So and then very efficiently, so that some operations may be efficient to implement in the curvilinear polygons or maybe pixelated representations. Some operations might be beneficial to use the B-spline representation. So it opened up new possibilities, I think.
Yeah, it's a great topic. I know there's going to be a Bacchus session on that later this year too. So I'm looking forward to hearing what other people have to say on this topic too. Okay, so let's move on to MRC. Speaking of MRC, so I also wanted to explain a particular idea that came out of Ryan Perman at PMJ in 2019. So the basic idea in curvilinear MRC is that, in fact, maybe it can be simpler. So the idea here is this is not actually what the computer algorithms do. This is conceptual explanation of what they would be doing. You take a circle or ball and you roll it around the inside of the curve, and if you can roll it smoothly without not touching one of the curves, then intersecting the shape, then you've succeeded, and this is MRC clean, so it's green, right? On the other hand, if you have a shape like this, where there's a protrusion on the lower right, then when you hit that ball hits that, it's going to stick out, and that's a red, meaning that's a MRC violation. You also would do the same thing with perhaps a different size blue ball here and roll it around the outside. And the outside shape might actually, in this particular case, it happens to pass through, but it might not pass that inside corner that's running through. And certainly when it hits the next door neighbor, that's a violation, right? As you can see. So there's probably going to be other rules that any given mask shop is going to add to this, maybe aspect ratio related, or maybe there's a separate rule that's about the minimum width or minimum spacing or something. But clearly something like this is going to be fairly universal in a curvilinear format where curved shapes are more natural. So what are your thoughts about this or any other ideas on is MRC going to be much harder on curvilinear, or what do you think, Ezequiel?
So I think it adds complexity. I think we're going to see clever solutions like you propose here, or maybe like Danping shared with us in the previous question by measuring radius of curvatures on B-spline curves. Certainly, we would need to have the tools develop to not only check for MRC violations, but also to repair them. I think that that's a key point that we don't need to forget, because today we rely on industry-wide polygon manipulation tools that allow us to perform Boolean operations and all sorts of data manipulation that allow us to fix the MRC violations once they are detected. But with curvilinear shapes, that could be a little more tricky, and we may need new functionality develop, and certainly that will create opportunity for a lot of new ideas and great efficient ways to perform these operations, which in the end is going to add to that turnaround time we were talking before, right? We want to make sure that this new capability that curvilinear masks will provide comes at the minimum cost possible as far as processing time. So efficiency would be key, and the opportunity for fast algorithms for these MRC checks, as well as fast repair of any violations, are going to be key.
Yeah, great point. Danping?
Yeah, actually, I differs from Ezequiel slightly. I think curvilinear masks actually provide opportunity so that we can simplify the mask rule, right? And we can simply rolling the balls, right, inside and outside. And I want to add that the two balls inside and outside may be of different size, right? So as long as when we roll the ball, we do not touch. We do not touch the other side, and also we do not leave the boundary, and then we are okay. So I think it probably provide opportunity for us to greatly simplify the mask rule for mechanical shape. For example, what we can do is we can compute the distance function, size up, size down. And then when you do size up, if you touch, like size up half of the radius of the ball, and then if they touch, we can check. If they touch, that means there's somewhere the gap is too small. And then we size down, and and then size up. So then we can check, okay, how far away after we do these operations, the new shapes compared with the original shapes, then we probably have a uniform way to check the MRC. So let me rephrase. So you do a size up by using exterior ball radius, and then size down, and then when you do size up, if the pattern is too close, they will merge, right? If there is some hole that is, let's say, they may disappear, right? So that size is too small, they may disappear. And then you size down further using the interior ball radius, and then you size up. So if you have an island, they may disappear. So this can be used to enforce the MRC, and also it might provide a way to efficiently checking the MRC. So the trick here is to be able to compute the distance function very efficiently. There are ways to compute the distance function, and we actually use that. But this is not the accepted as an industry standard yet. So I actually encourage maybe the EDA vendors to look into these approaches. It provide a uniform way to checking and enforcing the MRC.
Yeah, so there might be an opportunity to simplify because all those complexities that come from corners and
Yes,
corners
corner
running
to
into other
corner,
corners and all that
yeah,
stuff.
all those
Yeah,
complexities. Now it's gone, right?
Yeah.
So yeah, given my background is applied mathematician with a focus on level set method, and I my perspective of solving the MRC is purely based on mathematical algorithms. So there may be some other considerations like by the multi-beam mask vendor. So at least I propose this one, and I encourage the ED vendors to look into it and maybe implement it.
Sounds great. Thank you. Nakayamada-san, do you want to add something or?
Yes, through the discussion of all the points from Ezequiel-san and Daniel-san, I came up with one benefit we can expect from B-spline expression for DRC, especially for the curvature. If the shape boundary is expressed by analytic expression, then obtaining curvature from the analytic formula will be easier. But one downside may be the checking of intersection or the overlapping of two curves. Rigorously doing that may become more difficult compared to piecewise linear polygon inspection. However, if we choose carefully the order of B-spline, that might be easier too. That's why we adopted B-spline instead of nerves, which is non-uniform B-spline, to make the DRC easier. So we have a lot of things to discuss, and we should converge on the way of inspection in future as an industrial standard.
Great, thanks. So staying with Nakayamada-san, there's a VSP machine, right? And there's a proposal that Ezequiel showed the results of from Micron that talks about using VSP machines to do these curvilinear shapes. Maybe Ezequiel, you can explain what's shown here?
Yeah, certainly. This is a collaboration between D2S and Micron that looked at, like you say, extending the life of variable beam machines, variable shape beam machines, to write curvilinear mass densely, curvilinear masks. And the purpose of this work was to find the most efficient way to reduce the write time without losing the benefit of the curvilinear mask. So converting the curvilinear shapes into rectangular, more traditional shapes without losing the wafer performance. And the proposal was, of course, you can fracture the curvilinear mask and even apply like a shot reduction algorithm in order to reduce the write time on VSB machines, but that will in turn reduce the performance on silicon because it's blindly done. The purpose of this study was to co-optimize the shot reduction optimization with the IoT algorithm. So there was both a mask and a wafer simulation that was co-optimized such that the best possible performance was achieved, both for write time as well as wafer performance. If you look at the graph, the bar plot that's on the left side of the slide, what you see there is the number of shots for the different experiments that we run. And obviously conventional shots, when fracturing curvilinear shapes, the number of shots as a proxy for write time explodes. And what we see in the third bar, the mask wafer co-optimization, we see that the number of shots is only slightly higher than the conventional OPC, or what we would call our POR, process of record, OPC. But the wafer performance was similar or comparable to the full curvilinear IoT solution.
Yeah, thanks. So Nakayamada-san, this requires overlapping shots, and that's something your machines can do on the VSP side, right?
Yes, overlapping shots is not so difficult from writer's perspective. But the point is, like Ezequiel-san showed, inspection or assurance of wafer quality. That's the key factor in this overlapping shot technique. To achieve this level of mask wafer co-optimization, it needs strong collaboration between wafer fab and mask shop. So only a very sophisticated mask shop and wafer fab can do this collaboration. That's the biggest important factor for enabling this VSB shot, overlap shot writing on VSB writer to print curvilinear shapes.
Yeah, interesting point. So, Danping, you've been working on IoT for a long time, so you're familiar with this thought, right?
Yes, yeah, we spent a lot of time trying to reduce the shot count, right? I think today with the multiple beam mask writer, this is not a problem. The file data size may be a problem, but we have way to address that, right? So this is when we use VSB, right? A lot of our customers is still using VSB, and I think this is definitely very valuable work, right? To use traditional VSB to write high quality IoT mask. Yeah.
Yeah, but multi-beam would be better, right? That's easier.
But multiple beam, yeah, will be better. Will be better, right? But it costs money, right?
Yeah, yeah, exactly.
Yeah.
Okay. So last topic that we touched on earlier today. This is about curvilinear design. So we've been talking about using curvilinear shapes on mask to enhance the quality of wafer shapes. But the picture on the left is a poster that IMEC did in Photomask Technology 2019. And it's showing, it's basically saying that, hey, if we can have curvilinear shapes on mask, and if we can have curvilinear IoT, then that means we can actually have curvilinear target shapes on wafer. And if we could do that, then we can allow standard cells or memory designs or whatever to contain curvilinear pieces inside. That has a potential benefit, is what they were saying. And then we also saw in Ezequiel's presentation last year in this forum, shapes that look curvilinear, or at least very, very different diagonals, not just 45 degrees, but all kinds of angles. Maybe Ezequiel, you can touch on that and talk about curvilinear designs and what might be benefit there.
Yeah, absolutely. So I think this is an extension of DFM, or design for manufacturing, where given process constraints, you're trying to feed that up the chain to design layout in order to produce the target shapes that will both perform the best on wafer, will perform the best through the OPC flow, as well as provide the smaller footprint possible to pack as much information or line density or standard cell density as you can pack. What you see here is just a simple example of Micron routing layer for one of our NAND products. And what you see here, like you described, is multiple angles in line widths as we jog metal routes through a given part of the chip. And the purpose here, again, is to find that balance between the density of information you're packing per unit area, as well as maximizing overall process window. Having the ability to design in curvilinear space, or to allow for any angle in the layout, does benefit the OPC work and the resulting overall wafer margin or the wafer performance as far as process window and sensitivity to variation. So that's why you see this being deployed in many of our designs.
So you're saying it's not just for packing, it's also that if you target a shape that can be manufactured, that improves the manufacturing margin.
Yeah, let me give a simple example for those more familiar with lithography. Typically on a very low K1 metal routing layer where you have lines both in X and Y directions, you would be illuminating this plate with a quadrupole, kind of an aggressive quadrupole type of illumination. Depending on when you jump 1 or 2 tracks, this is a common layout technique. You may have jumps of 1 track to carry signals through the metal routing, or 2 tracks, etc. You may have different elbow lengths, and the natural ringing or overshoot and undershoot of the printed pattern will be greatly affected by that elbow length, as well as how aggressive your illumination is. And you can, of course, dial down the illumination settings or how aggressive that illumination is, but then the performance of the straight lines will suffer. That's when you introduce this angled jogs or angle track jumps, which not only allows you to make the layout more compact, but it does help tremendously with keeping the illumination aggressive to obtain the best contrast possible in your X and Y metal lines, and also avoid having to expand the space that it takes for that metal jumps or jogs that you see there. You can fit more of those jogs in a smaller amount of space by using.
Right. Yeah, that's for sure. That's very interesting. Danping, you talked about this in the beginning, but can you say again what you're thinking about for what this might enable?
I think the curvilinear design appear very naturally in photonics. We already see at SPIE some presentations by academia. So but the currently photonics design, curvilinear design, the feature size is very big. So we do not have any problem using the state-of-the-art, scanners to produce them. I suspect that when we go to smaller designs, during the place and routing stage, if we use curvilinear path, it's going to benefit maybe the timing, circuit performance, right? So I'm not an expert in that field, and then I do not have hard evidence, but I think nature does not have Manhattan shapes, right? That is what we invented for us to simplify our job. So when we print patterns on wafer, it's always curvilinear, right? Same thing as on mask. So why don't we go to what nature actually allow us to print? So I think this might be one direction to go in the future for the designers, and maybe we can squeeze a little bit more performance out of the circuit, right, by going to curvilinear. And I would suggest we start from place and routing, right? Start from there, and then that's might be the direction.
That's extremely interesting suggestion. Thank you for that. Nakayamada-san, what do you think?
Yeah, if curvilinear design or B-spline expression is adopted in the circuit design, there will be straight data path from the design to the writer in the B-spline expression. So we think, as Danping-san mentioned, we can optimize the structure one more time to skip some portion of the steps. And connect directly from one to the other.
Yeah, that would be great. That would there's nothing better than skipping steps to make things more efficient, right? So yeah, I agree with that thing too. I know a little bit about place and route, and you know, like if you look inside your brain, your neurons are not connected by Manhattan straight and lines, right? So you're right, absolutely.
That's right.
Nature would not choose to do it this way, right? So okay, great. So with that, let's wrap up this incredibly illuminating and interesting session. Thank you so much for lending your expertise to this new exciting topic. What do you think? Are we gonna go curvy or not? What do you think? Go ahead. Danping, you want to go first?
Okay, yeah, I have been working with IoT mask, curvilinear mask for almost 19 years, over 18 years now. And it has always been my dream to bring this solution, in my mind, it's very natural solution to high volume manufacture. So, but this journey has been turned out to be odyssey. It's very long, but I think finally we have all the pieces that is out there to solve the problems, and I think it's about time for IoT.
Yeah, thank you, Nakayamada-san.
Yes, as many of you know, our Multibeam was late, but finally, I think we caught up and we have ready to provide inline model-based MPC and B-spline new Curvy format. So please count on us, and we are very ready for the Curvilinear era.
Okay, thank you.
Oh, that's great. Ezequiel?
Yeah, I echo the same sentiment. I think throughout the forum today, we touched on many of the pieces that need to come together to enable this industry-wide. No question that curvilinear masks are here to stay. And certainly the OPC teams around the world will be taking advantage of this capability, because in the end, what matters is wafer performance. And certainly we know that curvilinear masks and curvilinear targets help us provide for better wafer performance. So no question that the adoption rate will be high on the leading nodes.
Okay, great. Yeah, thank you very much. Thank you, everybody. Okay, so that concludes this panel session. Thank you. Okay.
Thank you, Aki.
Thank you very much.
Bye-bye.
Stay safe,
Stay
everybody.
safe.
Thank you, everyone.
Thank you. Thank you very much.
Bye.
Bye-bye.